So actually, I will give the same talk like Shahrokh gave, just in a different approach, and also Péter touched plenty of things which I will touch also in my talk, and this just remind me that everything is connected to each other. So we always say that we need to ask a simple and important question. But let's start from the beginning, because we heard that Péter Ratcliffe wanted to be a chemist. He didn't want to work in medicine, but finally ended up. Shahrokh didn't want to do a doctor, but finally he ended up. So you can ask the question, why the pancreas? Why Péter Hegyi started working in the pancreas? I mean, I would say, who wants to work in the pancreas? I mean, nobody. I mean, I never intended to become a pancreatologist. Honestly, if you ask somebody who wants to be, I definitely didn't want. However, in '93, when I entered the laboratory in the Institute of Internal Medicine, I met an adjunct professor at that time, Tamás, who I am very happy to have him here also in the audience and accepted the invitation. And he actually inspired me a lot. He came to the department at 6 o'clock in the morning and showed me how to do the research, and 8 o'clock went back to see the patients. Until then, I continued the research he started, and he came back and we discussed what we have. But what surprised me, he didn't do it once. He did it every day. And I couldn't say never when I asked Tamás, I would come tomorrow morning, 6 o'clock. He said, I am more than happy to come. So the first message I would like to raise, find really, really a good mentor. And that time, I was working on in vivo models and wanted to understand how the pancreatic regeneration happening after that. And actually, I did my PhD in preclinical models. Okay, we discussed why the pancreas. So inside pancreatologists, the next question is, why the pancreatic ducts? Who wants to work with pancreatic ducts? I think nobody. So at that time, everybody thought that the pancreatic acinar cells who secrete the enzymes, they are the clever cells, and the pancreatic ducts are not. So when I went to my first conference, from 100 abstracts in pancreatology, 98 were submitted in acinar cells, and only 1 or 2 concerning this. However, again, in my second time in my life, I went to Newcastle with a Wellcome Trust Fellowship and meet again 2 brilliant mentors. And that time, the Newcastle physiology, medical physiology, was the #1 in the UK. And this inspired me to start working there. But when somebody told me it's me, just a little bit different way, that I felt I will be a plumber when I start working on the pancreatic ducts. So again, in the second answer, I never wanted to work in pancreatic ducts. But let's again ask the third question, why my first work started in the inhibitory mechanism of the inhibitory peptide substance P. How attractive topic. I think every of you dream every day to working on the inhibitory mechanism. So this was the third thing what I didn't want to do. However, and here is one message which actually came, that I had a burning desire to develop, to learn, to grow. And in the context I lived, I tried to find mentors, I tried to find institutions which can lead me. And after I said, if I learn the methodology, if I learn how to ask questions, what to do, then I can grow. And if you grow, later on you can ask your questions again. So at that time, let's look at in '99, when I joined exactly 25 years ago. And it's very interesting, the mathematics. It was 25 years ago. This is the 25th anniversary. It's 2025 today. Everything is almost 25. So at that time, when I joined to the pancreatic ducts, they thought that the pancreatic ducts is just provide a structural framework from the acinar tissue, and they convey the digestive enzymes to the gut, like a motorway from one city to the other city, like in the grave. Everybody loves the end and not the other part. So, but what we know, that the pancreas is the organ which provide bicarbonate. And a huge amount of bicarbonate, 140 millimolar bicarbonate solution, 1.5 liters, unbelievably lot of alkali. So at that time, the question arose, what are the roles of the bicarbonate-rich solution? And this is what was in the textbook. I think everybody in the room knows that our stomach secretes protons which make actually acid inside there. So everybody, I think nobody in the room who never felt an acidic burning part. And this is what we know, and what we know that with the food we eat, this food will go to the gut, and this acid is harmful there. So the pancreas secretes the bicarbonate in order to neutralize the acid coming down from the stomach. So it is very obvious, and after it became to be neutral, which actually helped for the digestion. However, I asked an extremely simple question. Actually, why does the pancreas secrete bicarbonate? If you looked at your picture, the acid going to the gut, and in the gut neutralize the acid. So why not the gut secrete bicarbonate? It would be so logical. The gut has bicarbonate transporters. So why the pancreas needs to secrete? And why the pancreas? Why not the liver? Why the pancreas? Why not other organs? So this question led me for 25 years research to understand why inside the pancreas is the bicarbonate important. But let's go to a high school first, because I started also in a high school, and let's have a chemistry lesson a little bit. We are in Monday, so we need to learn something. So here you can see a ductal cells actually in the picture, and here is, the pancreas, the acinar cells, and the ductal cells. So what's happening if you isolate these cells and you give CO2 and bicarbonate to the solution? The CO2 is a gas molecule, so immediately can enter the cell very quickly. When you give the solution, it's immediately enter, and what's happening there? The CO2 picks up the water, and after making actually H2CO3, and from this carboacids you will have hydrogen and bicarbonate. So immediately what's happening when CO2 enters the cell, actually you will have here hydrogen and bicarbonate molecule, so you immediately the pH drop down due to the hydrogen. And what's happening after that? The bicarbonate leaves the cell via transporter, so one ion, this is an exchanger, because this exchange two ions can leave via another channel, the CFTR channel, and of course you need other transporters which drives hydrogen out. This seems to be complicated, but you can see that due to the hydrogen and bicarbonate, if you measure the cell pH, you can see whether the bicarbonate leaves the cell or the bicarbonate stays in the cell. So this is the most important figure I will show you. So you can see a cell which pH level is around 7.4. So what's happening if you give CO2 to this cell, and ammonium chloride and bicarbonate? So ammonium chloride also can have ammonia, and ammonia can enter the cell, you know, very quickly. So if ammonia entered the cell, pick up a hydrogen, and bicarbonate stay in the cell. So if you give CO2 and ammonium chloride to the cell, you can see a huge rise in pH inside the cell. And after the cell tries to recover, and the cell recovers due to the fact that bicarbonate leaves the cell. So how to measure the bicarbonate secretion in the cell? You have to measure the recovery from alkali load. So what's happening if you remove ammonia from the solution? Of course, ammonium will leave a hydrogen ion inside, and the cell became the opposite, became acidic. And how the cell can recover that? The cell can recover it by restoring the pH level. So if you want to understand how the other side working, the different sodium hydrogen exchanger and the sodium bicarbonate co-transporter, this happening due to measure this recovery phase. So, and that was the place what I had a research as a Wellcome Trust Fellow in Newcastle. So this is a picture in Szeged. I was deadly frightened. So when I got the fellowship, we had no money for airplane tickets. I had the smallest car which we were able to boat in Szeged. So this is take the best of all of it, what Shahrokh said. So I sit in the car, I put all the baggages there, and through Europe, I went through 1,600 kilometers to achieve Newcastle. And of course, when I reached Newcastle, I was smiling because I never believed I will arrive to Newcastle ever, because when I went through the motorway, you know, between the big trailers with these small cars, I was not sure. But this is one thing, if you want the opportunity, you take it. You don't care you are flying on a business class or sitting in a small car and driving to Newcastle. So, and there I needed to learn techniques. First, I needed to learn how to isolate pancreatic ducts, how to do patch clamp on the ducts. However, I couldn't start working because there were challenges which needed to handle first. How we can correctly measure intracellular pHi? Because if I don't answer this question, all of my measurement will go to the bin if I don't measure it correctly. After that, my second question was, because these are epithelial cells like your skin. So in the skin, you have different transporters in the two parts. How to handle the two transporters together? I had no idea. And the third one, this was in room temperature. So how to make it 37? So without sorting these problems, you cannot do that. So there were three things, and I was actually very close to leave. And I just knew one thing, that I want to go home. So when I arrived to Newcastle, I didn't understand what to do. So I wanted. However, there was one serious problem. So Shahrokh also mentioned about money. Having less money may be your benefit. So this was the case. I had no money even to buy fuel, not only airplane ticket. So I stuck in Newcastle. I couldn't leave because I had no money, but I had a burning desire to go through. So this was one of the part when I stayed there and continue. And in this time, I asked how to solve the problem. So you can see a graph. You can see here three lines, what I showed you earlier, but you can see that the ratio, if you measure it in two different wavelengths, one cell, I looked at the papers, and in all experiments were on different ratios. However, at that time, in the physiology book, it was written that the pH equal with the ratio. So if you calibrate the system, one pH level, exactly one ratio. But come on, when I didn't look at the cells, but changed the shutter, you can see on the right side, immediately the ratio changed. So I needed to find out a mathematical model how to correct pH. So if you look at these three curves, I needed to get this one after the analysis. So we needed to develop a mathematical equation which seems very easy. I was working on it almost half a year. This is a picture at 3 o'clock in a.m. in morning when I tried to find out how to do it, and there were no mathematicians around me. There were no AI. I was on my own to find out how to measure it. The second problem was how to learn microperfusion, and that time on pancreatic ducts, nobody did microperfusion. So I needed to fly, but at that time Wellcome Trust supported it, to San Diego to see Paul Quinton professor who did it on sweat ducts. So I needed to learn how to do, and I asked Paul, where can I buy the pipettes? And he was smiling. He said, you cannot buy it. You have to make it yourselves. Me, as a glassware expert who is doing, and also the microperfusion technique, exactly the same, I had to put it on to start the experiments. So I immediately became to be a glass technician. So I wanted to be a medical doctor. No, I became to be a plumber. After I became to be a mathematician. And finally, I come to be a glass technician, a glass blower. And I still couldn't start the experiments yet. So the third question rose, how to provide 37 Celsius. So I went to the lab and went to Barry Argent professor, and I told him I saw in one company selling it for 10,000 pounds. He said, Peter, all grant is run out. I'm so sorry, I cannot provide 10,000 pounds. Do whatever you want. And this is my third message. Again, it was touched by Peter and Shahrokh as well. I looked around the lab. What we have in the lab? There were very cheap tubes. Okay, we have very cheap tubes. We had a heating bath. We have actually there the microscope. So I started building a new heating system for a couple of pounds where you can put the hot water, but it was important that the water, if it goes from that way, this will heat up everything. If it would come that way, it would be cold. So I had to play a lot how to set it up, but finally I could make a system which from a cold solution to make exactly 37.8. So actually, I got a heating engineer position at Newcastle upon Tyne as a Wellcome Trust Fellow. So now, after doing this challenge, which took almost half a year, it was time to start. So at that time, we did lots of experiments to look at, and this is what I mentioned, that secretin is a peptide which you can stimulate the secretion, and I could see that this peptide closes it. And actually completely block the effect of this neuropeptide. And we did another lots of experiments to look at which transporters are involved, and the transporters on the other membrane were not. So we were very sure that actually the neuropeptide substance P block the bicarbonate secretion inside the cells. And we also could see it's a dose-dependent way. In pharmacology, you may already learn from your teachers, you can see a saturation, you can see actually the way how the different cells acting, and now this was the time when we were sure that the pancreatic ducts not only have stimulatory pathways, but also has inhibitory pathways. So this is the first thing I felt we discovered something, that we not only have a single secretory pathway, but inhibitory one. And with my friend who also went to Newcastle after that, Zoltán Rakoncai, who you know very well, he was also the one who he actually looked at this methodology. And as Shahrokh mentioned in his, I think it was number 10 or number 9, when you showed publish, publish, publish. So we first wrote down that the pancreatic secretion has a complex inhibitory mechanism inside the pancreas. So discovering both stimulatory and inhibitory pathway told you that there is a complex physiology which balance much responsible for that. So this is the first thing I think we discovered and showed, that if you eat, like the lunch today you've taken, you eat, you will have a stimulated secretion for your acid secretion and also for your bicarbonate secretion. But it's not stopping by chance. So it's not stopping because you stop eating, it is stopping because somebody's switching off. So this is our very first discovery, that the pancreatic secretion, like the acid secretion, is not only a mechanism which is switching on, but there is a mechanism which is switching it off. But, as you know, I had a very serious question. Why does the pancreas secrete bicarbonate? So we discovered something, of course it was important, but I'm interested in another question. So sometimes when you have a basic question, you don't get answer immediately. You get an answer to another question, but what is important to keep it going? Don't say that I couldn't answer the question, but I answered something else. So as I told you, I was a medical student. I became to be a young researcher. I became to be a mathematician. I was a glass blower. I was a plumber in the pancreatic ducts, a heating engineer. But I completed the medical school and started seeing patients as a medical doctor. So I put to another position. Plenty of people saying that being a clinician or basic scientist is a must. I say the opposite. You have to understand what to do, and that time as a clinician, I forgot ducts for 3 years. And I started concentrating on the patients, and I started looking at the patients on the bed with acute pancreatitis. So we just discussed that what is in the textbook, that the pancreatic acids secrete the enzymes which eating the food, but they are inactive. Because if it would be active, it would eat your pancreas. But when the bicarbonate secreted and this enters the gut is clever. And the gut secrete enzymes which activate it. So it's a brilliant system. The pancreas secreted in an inactive form, and it became to be active, actually, in the gut. And why is it active? Not by chance, because the gut wants to eat active, and this is why it secretes, actually, enzymes. But what's happening if there is actually a stress on the pancreas, like alcohol, bile acids, smoking? You know, the enzymes activated inside the cell, and there is an inflammation and cell death and the whole process going wrong. So if the autodigestion happening inside the pancreas, you get pancreatitis. This is the reason why everybody were concentrating on the acinar cells, because they believe that trypsin is the most important part. And the incidence rate of pancreatitis is tremendously growing. In Hungary now over 5,000 patients are affected. In the US, 250,000 patients affected. And in the mild disease, the mortality rate is low, but in severe pancreatitis, still 20 to 40% of mortality, and no specific therapy. So I was standing next to the patient side and couldn't do anything. So I said, I cannot treat the patients well, like Tom Zudoff said in there, because I am incompetent. But I am incompetent not because I don't want to treat my patient. I was incompetent because there were no knowledge, there were no discoveries. So I had to go back to the lab. So this is extremely important as a clinician, to going back to the lab and continue the story. And also Péter and Shahrokh mentioned that this is, we put the stories next to each other. It just doesn't happening that you are sitting, ask a question and answer it. And here is a brilliant UK physiologist, Peter Thorne, who actually published an article, and this article, he measured the pH inside the acinar cells, and he discovered actually that the acinar cells secrete acids. Nobody knew that before. That the acinar cells, here you can see this the red line, not only secrete the enzymes, but secrete acid. This was a tremendous discovery in the field. Why? Because if you think where the pancreatic enzymes activating, it would suggest that if pH has an effect on the trypsinogen autoactivation, that could cause problem. So based on Peter Thorne discoveries, we built up a next story, and I started to have an idea, why does the pancreas secrete the bicarbonate? And I am also very happy that many of my PhD students are here today, and one of those is also here, Petra, who did these kind of experiments, which at the end of the day, it's turned out that if there is a problem with the secretion, the pH dropping down. And Andrea Geis, who is now in Boston, did the experiments, a very easy biochemical study, a very easy activation, autoactivation of trypsinogen. So, if the pH is 6, you can see a very quick autoactivation. Look at the time. Within 30 minutes, the trypsinogen is activated. Within 30 minutes. Usually 1.5 hours, how the trypsinogen leave the pancreas. So, however, if you look at it in pH 8, it's completely almost inhibited. So this discovery answered the question, why does the pancreas secrete bicarbonate? So, and one of my major achievements that the Ole Petersen, who was working tremendously on acinar cells, and at that time, people in acinar research never believed the role of bicarbonate and the role of duct. When I went to a European Pancreatic Club conference, I had one abstract in duct in the back, and there were 90 abstracts there, and people come to me, Peter, why you are working on the ducts? You will get nothing out of it. You should work on the acinar cells. And finally, I could convince Ole Petersen that really the bicarbonate secretion is extremely brilliant, and this is what now in the textbooks concerning the pancreatic acinar and bicarbonate secretion, that the acinar cells secrete the enzymes in an inactive form and acid, and this is the role that the bicarbonate secretion by the ductal cells make it. And after that, now if I answer the question, why does the pancreas secrete bicarbonate, I got the answer for maintaining the intrapancreatic homeostasis by keeping trypsinogen in its inactive form. But from Wellcome Trust, I came home from Hungary, and this is what András already mentioned, that without the help of Department of Pharmacology, I would never be able to continue my research. And the second very important was, like Brian Kobilka mentioned in the video, that you need grant to start. And it's highly important for young researchers to provide grant to start. And I received the Wellcome Trust Initiative Research Development Award. András provided the equipment, and I could buy the necessary things. And that time, we started investigating the pathophysiology. And here, Victoria Wenglovec, who was Vicky, my very first PhD students, and ask again a simple question, how bile-induced pancreatitis is developing? But we had the system at that time, because we actually built up in Szeged this microperfusion system, so we could put bile into the duct, and you can see, you may see already how a cell looks like. You can see this kind of intracellular organelles. These are called mitochondria, and they are the one who secrete ATP. These are the ductal cells. You can see the nuclei, and here is the cell. You can see a tremendous amount of mitochondria. This is a mine. This is the pancreas needs almost the highest amount of energy in the body. You cannot see more amount of mitochondria almost in tissue like in pancreatic duct or acinar cells, because you need ATP to work for enzyme secretion and pancreatic duct secretion. So what we found, however, also actually in Szeged and in the acinar cells, they also found it, if this mitochondria and ATP are extremely important for the process. So of course we also wanted to see how the process going. I don't want to go to the details very much, but we measured intracellular signaling and we could identify a toxic calcium signal, which everything is good in a low concentration. If you drink one bottle of wine, you are in trouble and you will get this signal. If you just a little bit stimulate your body, then you can have an oscillatory normal calcium signal. And we also looked at plenty of confirming experiments, whether this is intracellularly, it's a dependent or independent process. And this was the other hallmark paper we provided, that one of the key moments in pancreatitis is the mitochondrial injury, and this is also, I'm very happy that József Malét, who is a key investigator at Szeged University, still in the field, provided the experiments that showing that how bile acids killing the mitochondria and providing an EDP dop. And also you need intracellular experts. We were not bile acid experts, but we had two highly important clinicians, Stephen Keeley and Alan Hoffman. They were tremendously expert of bile, and we could put together how the bile induce actually diseases, what kind of receptors are involved, and how to treat actually these diseases. So let's look at genetics. Is always very important to confirm your idea. So we had another student, Anita, and everything showed that this is the transporter, this chloride bicarbonate which is involved. And I was fascinating, I was sure that this is. So it was one of my first hypotheses which were completely wrong. But I tried to prove that I am right. And we did a huge genetic cohort to show that these channels are involved, and the experiment showed clearly it's not. So after that, when I know listening plenty of philosophies like Seneca, Marcus Aurelius, there is one quote: you stop proving yourself, start improving yourself. And this is a very important quote. You have to give up a hypothesis which is wrong. So the other fact is, however, I like reading old papers. And this is what I suggest all of you to read old papers. And this is one of the papers what we read at that time, how alcohol actually affecting of the CFTR. This was done in '65 by Henri Sarr, the Marseille pancreatic group I mentioned when I introduced Shahrokh. Is a brilliant observation that they were the very first to show in '65 that they could see a plug inside the pancreatic duct, a mucus plug. And they wrote down that this mucus plug is very similar to the mucoviscidosis. So CF Kids has a very salty sweat. He very elegantly measured the sweat salt concentration for the adult alcoholics, but at that time the CFTR gene was not discovered. So he just wrote one short sentence in the discussion that he doesn't understand the whole process, that's why this is like a complex mechanism. So however, '89 they discovered the CFTR channel, which is responsible for pediatricians for CF disease. So I asked my students, and this is what Shahrokh mentioned, have a brainstorming with the students, what to do, how to prove it, that alcohol can have an effect. We saw from the experiments of Henri Sarr that patients who drink alcohol, actually their sweat will become salty. So I asked my students what to do, and they said, Peter, we have to do a study when all students drink alcohol. I said, come on, I cannot send the Welcome Trust money. I'm buying vodka, you know, and drinking. But they said, Peter, this is the only way to prove that if you drink alcohol, your CFTR is decreasing. We need to measure the sweat concentration in your body. So, okay, if it's your idea, so I sent an ethical approval, and that time the ethical approved for 10 people. So I came back from the ethical committee meeting to the lab, but by the time I arrived back, 9 of my students signed the consent form that we will do the one. But they said, Peter, we left one consent form for you because we want to see you drinking alcohol. So the challenge was extremely, we had to drink 400 milliliters of vodka in the study to test the hypothesis, it works or not. So I spent my Welcome Trust money. Maybe Peter Ratcliffe is not in the Welcome Trust board continuously, but I spent my money on vodka. So we drank the vodka and measured the sweat colloid concentration. I never ever organized a study what everybody loved. All the lab, look at them, they were laughing, they were one. However, what did you see? That it didn't work. They could reach a 20 millimolar concentration, but there was no effect. And my students were smiling. And I asked them, why are you smiling? Because, Peter, do you remember what did you say last week? No, I don't. When we had a failed experiment, what? Repeat it. So, Peter, please go and buy vodka again for us. We enjoyed the experiments very much. But I said, if we keep going the same things when we were failed, it will not work. But Szeged is a very good city. But now when I went to Péter also a very good city for experiments. Newcastle is a very good city. Budapest, very good city, because we have volunteers who are willing to drink vodka without I buying them from the Welcome Trust money. So then, I told to my student, let's go to speak with them and look at them. They said, we don't need to speak because they are by the ambulance car, they are taking to the ER unit, and we just need to measure it. And their sweat colloid concentration was extremely high, so this was the measurement in which we proved. However, when we submitted it to the journal, they said, Peter, it's rejected. I said, why? Because you didn't prove that their alcohol concentration dropping down after the CFTR channel starts working again. So my students on the Szeged streets were walking, following these guys, and looking at when the alcohol concentration dropped, invited back to the lab and remeasured it, and the effect was very clear. It partially could have been defended. And this is our second hallmark paper. We are the very first who showed that chemicals like alcohol, bile acids, and later on smoke extracts inhibiting CFTR. Of course, we did lots of experiments, and I just show you that we did histology, we did chemistry to show the data, and I really don't want, I just show you to go to the details, but I would like to show one experiment actually here, when you have the cells and we measured the CFTR chloride channel when we looked at the fatty acids, and it's almost switched off the CFTR channel, so almost killed the channel's activity. Of course, there were plenty of experiments we did in different places, like we had no small animal MRI in Hungary, so we went to Germany for a team in Greifswald who had small animals MRI, and we looked at the pancreatic secretion, so we could prove that not only intracellularly the bicarbonate secretion is stopped, but also the secretion is stopped. So we went further, and we also, this is what András Varró showed you, we could identify the trypsin vicious cycle, which meant that inside the cell, if the bicarbonate stopped, the pH dropped, the pH will actually auto-activate the trypsinogen, it stopped the secretion, shut down the CFTR channel, and this is the major drive of how the pancreatitis actually developed. So I knocked on the door again on my earlier supervisor, Tamás Takács, who is a brilliant clinician and can do ERCP. And I asked Tommy, would you measure the pH when you do the ERCP inside the pancreatic ducts? And I said, why not? So we went there to look at whether what is true in the cells, what is true in animal models, whether is it true also in human. And when we measured it with only 6 patients, it was very clear that here is when the bile pancreatitis starts, and here is the measure of the time. Those patients who had pancreatitis, the pH was 6.97. Those who had no pancreatitis, 7.8. So this was the very first confirmation in the literature showing that in human, this is exactly the same situation. And now we know do ERCP to remove the stone, and this is actually, this regression curve shows that it really does matter when you do the ERCP, and we had the protocols that if there is an inflammation with cholangitis, pancreatitis, you have to do the ERCP as quick as you can, and this is one of the reasons for that. And of course, we had another experiments concerning understanding how the smoke extracts, and this is good if you move. Like I moved to the University of Pécs, and here is Zsuzsanna Helyes, who I also had a word with. Zsuzsa, you had a very good system to smoke the small animals. Let's continue and let's work together. And I also don't want to go very much to the details, but we could show that the smoke extracts had the same effect. And the final confirmation was, here you can see, this is human patients. We can reproduce what was in 65, that in chronic pancreatitis, you can have this mucus plug inside the pancreatic ducts, and we could show it also in experimental models. And this is actually, if you measure the fluid secretion, how big is the pancreatic ducts, you can see that the secretion is really decreasing. So if you get a pancreatitis, by week 4, you have almost no fluid secretion. So what we could show, that activity of CFTR, bicarbonate secretion and fluid secretion dropping during pancreatitis, you will have mucus, and exactly the same what you can see in pancreatitis like in CF. And this is actually the vicious cycle we published, that this whole process actually keeps the pancreas growing. So again, we need to write it up, and all CF experts in the field agree tremendously that there is a new horizon of treating pancreatitis by CFTR activators and potentiators. So our main question, if these kind of cystic fibrosis-like changes, you could see that there is a new drug in CF which can be used, whether this can have the first therapy actually in pancreatitis. And again, I went back to the lab. So you have to understand that you can be a clinician, you can be a scientist, and you can move forward. And this was also one of the hallmark experiments when we used CFTR activators and we used potentiators. Look at, this is alcohol. The CFTR channel almost switched off. And look at this. Actually, this kind of combined therapy immediately restored the effect of alcohol. And again, it was showed that you can see a pancreatitis-like effect. If you give the CF therapy for small animals, this is restoring the effect. So, what I told today is it's 25 years of research experience which showed that both stimulatory and inhibitory mechanisms are existed. Also that bicarbonate is extremely important to keep the pancreas in a physiological state. We proved that CFTR is the key factors, and CFTR modulators actually is one of the target. Now what is the next step? Use it in human. And actually when András referred that I moved from Szeged to Pécs, this was one of the main reasons of my movement, because the University of Pécs provided opportunity to actually work also in the clinic. So this is a hallmark importance of our translational project, know how to turn scientific knowledge actually for society benefits. However, the translational medicine model we know from bench to the bedside, and later on the T0, T4 project, this took around 17 or 24 years. So I looked at my age. I am all right. I'm 53 and I'm in a good health. But should I wait 24 years, you know, to go to the next stage? No, I don't want. I want it. So we needed to develop a new model, which we call a translational cycle model. And this was the second time when I went back to András Varró, and we also discussed it with the Academy of European members, what kind of models we can do. And the model was simple, like Péter's model as well. You be a clinician, ask the questions, go to the lab, have the knowledge, and this cycle, if you bring it back, this would be actually beneficial. So we published our work in Journal of Physiology, which actually the chief editor also find it the best of the month article. And I went to Vertex because they are selling the drugs. And if any of you became to be a member of the pharmaceutical companies, please remember this story. One drug is $300,000. You cannot do research. How can I test it without a company? I can't. And no Vertex, because they have until 2030 the right for the product. They don't want to risk to get any of the side effects on the drug. So they said to wait, but we didn't want to wait. So we actually started another study, the Gulyás study. I don't know whether what you had for lunch during the week. That Gulyás is general utilization of energy back to the cells. We tried it with enteral feeding to provide the results. Or my students are extremely creative. The other study name was Elephant, because you need to eliminate fatty acids from the cell. So besides having no drug, we still try to find. So what I am really proud of, not really the experiments, but the students I could gain. So during my career, I could train 29 young fellows. 1/3 of them are here today. I am very thankful for them. And I looked at what happened with them. I asked from them by email a question. I am very happy that around 60% of them stayed in science. And they provided, after the PhD training, over 200 papers. And now they have much more PhD students than I had. And they received plenty of independent research grants in there. So what I am proud that I said, if you get older, you are thinking differently than youngsters. When I was young, I was sure in everything. No, when I am older, I adopt in everything. So I said, when I am out of the competition, then what's left after me? No, I am very happy that to seeing them that they are actively doing research. And PhD students, the other things I am very proud, that I visited Newcastle this year in January. And I showed you the water system I built up 25 years ago. And this system is so effective that 25 years later, the students actually using the same system I built up in 1999. The 8th generation of the students are still using it. So these mechanical things, I think it means. I'm also very thankful, of course, for all grant agency who provided me, and of course my family, where not only my kids are there, but of course somebody needs to teach you. You need a mother who is, even when you are 52 in a summer holiday and you don't clean your mouth after eating, she goes to you and clean it, and I am very happy that also she is here today for the meeting. So what I learned during the day, it's not important how much you like to be. I wanted to be like a well-being gynecologist. What matters that you need to learn and grow. Choose places where you can earn experience and knowledge. So I went to the lab in Szeged, I went to Newcastle, I went to San Diego, I went to Boston, I went to Liverpool. The fanciest projects sometimes lead nowhere. It's the same. So what you need, the greatest success from my theories sometimes came from the most difficult ones. And of course, you need to understand and what are you willing to do. From the moment I was driving with the smallest car to Newcastle, ask yourself, when you come to science, are you willing to work on your question for 25 years? Do you like it? Do you have the burning desire? Surround yourself with excellent mentors and excellent collaborators. More than 50% of the work you show today, they are done by not in our lab, but in different labs. Without collaborations, you cannot reach anything. So you need a team and excellent young people, and you need a system-level solutions. If something doesn't work, you cannot handle it individually. You must handle it as a system. So I was thinking, because I was at the age of 30 when I learned basic physiology. Like approximately 14 years later, like your age currently. So after my research experience, when I learned the physiology at the year 30, I had no more questions, because I knew that we need to establish a system for young people which can reach excellent mentors immediately. I immediately knew that we need a system which is a multi-generational and can handle you from the beginning to the end. We needed to provide opportunity to anyone. If I look around, of course, I don't see it, but I saw the list of towns and villages you came. You came from Zalaegerszeg to Kisvárda, from Győr to Szeged. There is no county today here which is not represented by young fellows, and we needed a system can do this on a large scale. And somebody asked, what was the major benefit of my research experience with the international network? I would say that this is the National Academy of Scientist Education. Thank you very much for your attention.
Ask for questions. Okay, over there.
Thank you. Okay. Thank you. As I could understand it, you mentioned a significant point in the disease progression, which is when the acidic surrounding destroys the mitochondria. Would you be so kind to explain why that happens, or provide some pieces of information about that process?
Thank you very much for your question. It's extremely important. So the cell responds for everything you administer for it. So actually you need it to understand what's going on. If the pH drops down inside the cell, you always have other intracellular signaling, and one of those of the calcium signaling, which means if the calcium rising, you can see. And if the calcium rising in a tremendous effect, then inside the cell, you can actually see a toxic calcium signaling. The other way around, the protons, how the protons can stimulate to activate trypsin. The trypsinogen has two major parts. One of them is the active part, and one of them which is actually stopping it. So if you give proton, you actually broke it, and after this hydrolysis, you will have the active form, and this will switch on the trypsinogen activation.
Further questions? Further question, then I would like to thank you, Peter, for your excellent talk, and I would like to give you the medal and the diploma. This is